오늘은 좀 과하고 뭐 내일까지 해라.
아, 네, 알겠습니다.
답답한 면이 있지, 그지? 숙제는 내가 냈냐? 아, 일단 뭐 하는 대로 하면 돼. 알겠다.
알겠습니다. 네.
오케이. All right, let's just start. Today, we study the active component. Okay, so we're gonna go through the operation of BJT and MOS. Especially, we use silicon germanium HBT. Also, as a RF and analog circuit designer, understanding of MOSFET is critical and essential. Okay, so we're gonna cover it. So people just consider BJT and MOSFET as a three-terminal charge control device, right? That's true. However, as you guys understand well, the BJT has actually, the characteristic of a minority carrier current diffusion, right? So the operation mechanism is diffusion current, right? For a while, MOSFET is operating based on the drift current, right? That's a huge difference. Okay, so since the minority carrier changes exponentially depending on the forward bias voltage, right? If you take a derivative on the exponential, then it's also exponential, right? So because of this reason, if you change VBE, then the current will be changed exponentially depending on the VBE. Okay, that's why the operation equation of the BJT is given like this way. Let me just write down. So IC equals IS exponential VBE divided by VT, right? So this is the reason, because charge, minority carrier changes as a function of exponential VBE divided by KT. Right? So if you take derivative on this, then you get this, because this diffusion current is basically expressed like this way: dx and d diffusion x. Right? So initially, this n is n0 and exponential Vt and Vbe, and it also a function of actually minus L and X, right? But this is this doesn't matter, because we just use collector as a reverse bias. So diffusion characteristic is modeled like this one, right? So this slope gives based on this relation, this slope gives exponential Vt or Vb. Okay. So for the MOSFET, because its mechanism is drift current. Drift current is given by area, right, multiplied by J drift. This A is if you draw the channel in three-dimensional way. Let's say this is channel, okay, channel, and this is a drain, and this is a source. So the area A is actually width multiplied by thickness of the channel thickness. Okay, so here J drift is given by Q, right? And number of channel and channel and channel, and this is low V, right? Low V, and multiply by velocity, which is mu and electric field, right? So eventually this can be given by Q and channel and mobility mu and electric field E, right? So approximately we can just say electric field between this and this is L divided by VGS when it is in saturation, because okay, VGS minus VTH actually, because there is no channel at all if VGS is less than threshold voltage. And when it comes to this, right, QN and here W and T channel, right? So if you take a look at this, let me just take out this, then QNT channel, right? QNT channel is actually speaker. This is a charge per meter square. Okay, this charge per meter square is actually Q equals CV, right? So C here, C is what? C is a Cox, right? V is applied voltage, V gate source minus V threshold, right? So the total charge is just if you take a look at this, this is actually farad per meter square, per centimeter square, right? Per centimeter square. So which means this Cox multiplied by VGS minus VTH itself is what? The unit of this is what? Unit of this is actually Coulomb per centimeter square. Okay, this is Coulomb per centimeter square, which is exactly the same with this Q and T channel. Okay, so as a result, right? So J drift was a Q N channel T ox T Q N mu, and this is a T channel, right? So this is given by Q N channel and T channel and mobility mu, and this is L divided by VGS minus VTH, and as we observed before, this is a Cox multiplied by VGS minus V threshold. Okay, so in saturation, right, we assume that actually speaker total charge is triangular, not square. Therefore, we have to multiply it by half. Okay, so that's why ID is given by half of this is mu Cox. This is a VGS minus V threshold scale divided by L, and it's W, right? The only thing left is a W. Why? Because this is a total channel, and here is a A is WT also, right? So W. That's why we get this. Okay? This is the simplest way of deriving, current in the MOSFET in saturation situation. Okay, so for more, accurate derivation, you have to take an integration, right? But considering the, limited time, I will just simplify like this way. 이해했지? 여러분들, 그지? 자, 간단하게 이야기하자면 뭐야? BJT는 디퓨전인데 디퓨전에서 중요한 건 마이너리티 캐리어란 말이야. 마이너리티 캐리어는 베이스 에미터에 인가되는 전압의 익스포넨셜하게 비례해. 그런데 마이너리티 캐리어 디퓨전 공식이 이 마이너리티 캐리어를 미분을 한단 말이야. 미분을 해가지고 디퓨전 컨스턴트를 곱하면 J란 말이야. 근데 이 값이 뭐의 함수냐면 익스포넨셜 VB의 함수이기 때문에 이걸 미분해봤자 X로 미분해봤자 맹 익스포넨셜 VB의 함수야. 그래서 이게 있는 거야. 그럼 이 뒤에 있는 거는 상관없어. 왜? 우리는 지금 BJT에서 베이스 콜렉터 단을 리버스 바이어스를 가하기 때문에 이렇게 되거든요. 이게 아주 짧아. 그래서 이건 상관없는 거야. 이 슬롭이 그냥 approximately linearized 돼가지고 상관이 없어요. 그래서 아주 쉽게 우리가 이것임을 증명을 할 수 있어요. 모스펫 같은 경우는 어떻게 된다고? 모스펫 같은 경우는 드리프트 커런트가 메커니즘이야. 그러면 드리프트 커런트가 J 드리프트 곱하기 에어리어인데 이 에어리어는 위스 곱하기 thickness of 채널이야. 채널 thickness. 그러니까 이렇게 계산이 돼. 근데 J 드리프트는 어떻게 돼? 로 V잖아, 로 V. 로 V고 V는 뭐야? 로 곱하기 뮤의 일렉트릭 필드야, 그지? 근데 우리가 세츄레이션인 경우에 고려를 하니까 이게 세츄레이션이 되면 VDS가 언제하고 똑같아? VGS-V 스레시홀드 볼티지하고 똑같잖아. 그러니까 일렉트릭 필드는 VGS-V 스레시홀드 볼티지 나누기 L이 되는 거야. 세츄레이션이니까. 그러면 남아있는 건 로인데 로는 뭐야? 로는 했잖아. Q의 N채널 이건 유기되는 채널이야. 인듀스더 되는 채널이야. Q의 N채널에 어떻게 돼? 모빌리티 이렇게 되잖아. 그 다음에 thickness, 그 다음에 width 이렇게 돼. 그지? 자, 그럼 여기 잘 보면 QN 채널 thickness를 봐봐. QN 채널 thickness는 요 W를 빼고 QN 채널 thickness는 요거는 지금 차지 퍼 미터 삼성, 센티미터 삼성이고 이거는 센티미터란 말이에요. 그래서 이거는 차지 퍼 미터 제곱이야. 그러면 이거는 뭘로 표현할 수 있냐면 Cox의 VGS-VTH로 우리가 어프로치메이션 할 수 있어요. 왜냐면 캐피스터거든, 결국. 캐피스터에 인듀스 되는 차지하고 채널 내의 차지는 똑같을 거 아니야. 그러니까 Cox VGS-VTH라고. 그런데 토탈 차지가 우리는 어프로치메이트 하기를 이렇게 스퀘어라고 어프로치메이션 했는데 실제로 저거일 때 세츄레이션일 때는 이게 삼각형이란 말이야. 삼각형. 그러니까 실제로 차지는 이거의 반밖에 없어. 그러면 어떻게 돼? 이거를 집어넣으면 되잖아. 이게 뭐하고 똑같아? Q의 N 채널, T 채널 이거란 말이야. 그러면 끝났지 뭐. 다 집어넣으면 Cox의 V 게이트 소스 마이너스 V 스레시홀드의 2분의 1에 그지? 그 다음에 L에 W 있지, 그지? 그 다음에 뮤 있고 그 다음에 이게 VGS 마이너스 V 스레시홀드. 그러면은 뭐야 이게? 결국 이거잖아. 그래서 이렇게 유도가 된다. Right. Let's consider silicon germanium process. Okay. Recently, silicon germanium process has been widely used since device characteristic in HBT is superior to MOSFET, that of MOSFET. Okay, especially RF performance is much better. We consider RF performance. We evaluate the RF performance based on FT and Fmax. FT and Fmax. For example, IHP, IHP 0.13 micrometer silicon germanium processor has FT approximately 400 gigahertz. Fmax approximately 500 gigahertz, something like that. Okay, it's 350 something. Anyway, as a ballpark number, the values are around both. Okay, so typically there are one or two very thick metal layers. We call this as a UTM, ultra thick metal layer. Okay, and more importantly, the thickness of back end of the line, the oxide, it's not exactly oxide, the dielectric thickness of this back end of the line is about twice of CMOS counterpart. Okay, it's 12 micron. Why is this important? Because if dielectric thickness is, thicker than the dielectric, the loss caused by this losses substrate will be drastically reduced. And also, more importantly, on-chip antenna, okay? When you design on-chip antenna, this high thickness provide much better radiation efficiency. This is very important, okay? Especially for D-band, right? D-band TRX, right? We need to integrate on-chip antenna, right? Since on-chip antenna, the radiation efficiency of on-chip antenna is directly related to the thickness of dielectric material. Why? If the thickness of substrate is thin enough, then this is looking like a capacitor. Okay, since it is a capacitor, all the energy is confined between these two, confined inside of this dielectric material, because electric field between two is too high to radiate. Okay, that's why we need to have a thick BOL layers for better on-chip antenna. Okay, unfortunately, this is money. This is money. Okay, so for silicon, for CMOS application, right? We typically, keep this less than 5 to 6 micrometer for CMOS, which means this, if you implement an on-chip antenna in CMOS process, the performance, especially the radiation efficiency, is not that good. Okay. Okay, let's discuss the BJT operation. Okay, different from HBT operation, different from the BJT, right? So typically the beta, right? Beta is consist of emitter injection efficiency multiply by actually alpha, right? Alpha is proportional to emitter injection efficiency. Okay. Also, beta is what? Beta is 1 minus alpha and alpha, right? Which means if alpha is close to 1, then beta is infinite, right? This is what we want, right? We want to have a BJT with a largest possible beta. Okay. So to improve emitter injection efficiency, right? For conventional BJT, right? What we do is, let's say this is a emitter, and this is a base, and this is collector. What we do is we provide a high ion implantation, right? So we just make this is a P, and let's say this is a N plus 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 plus, and this is a N, right? We provide a high, ion implantation, high impurity to the emitter, right? So the problem of this, while we provide a very small amount of, impurity implanted on base, right? The reason of doing this is to improve emitter injection efficiency. We need a larger amount of, diffusion from emitter to base. The minority carrier in the base is what? Electron, right? Electron. So to improve, this as we observed before, right? The amount of this minority carrier is given by this Ni square. No. Ni square divided by Na, right? Na, and exponential Vt Vbe, and exponential L x minus 1, okay? Which is something like this, okay? That means to improve this, right? To improve this, we need to make impurity density in the base small, right? If you make impurity level in the base small, then the injection efficiency will be improved. Since this is a relative, right? This is a relative, so this also means that if you just make a high ion implanted on the emitter line, so the minority carrier, which is a P hole, right, in the emitter side is this is ND, and this is Ni scale, right? So we need to make this a small line. So we need to make this high, okay? So that's why we implant high at the emitter. We implant, small at the base, right? To improve emitter injection efficiency. However, unfortunately, if you make like this way, then resistor in the path of base, RB, increase drastically. This is very bad for the Fmax performance, because Fmax is proportional to Ft, 8, pi, RB, CGD, PC, right? Something like that. So this is a directly inversely proportional to RB. So for the BJT, RB is high, which make Fmax small. However, if you make silicon germanium, if you use a silicon germanium as a base, then this energy band gap becomes smaller. Okay, just look at this BJT, which is silicon. So this is much small, right? This is 1.12, and this is 0.6 something, right? Much small. That means the slope over here is reduced, which means emitter injection efficiency is improved quite a lot, right? Also, the hole, when it comes to hole line, for the BJT, there exists, I mean, for the HBT, there exists a barrier, large barrier. This barrier, the extra barrier is caused by the energy band gap difference, right? Which means delta P is reduced by this barrier amount, which is proportional to exponential the amount of barrier, right? So that means the hole density is reduced quite a lot, while the electron density is increased quite a lot. Okay, so because of this, band gap difference, emitter injection efficiency is very very high, even with a high impurity, high ion implantation at base. Okay, if you provide a high ion implantation at the base, that means the RB is drastically reduced. Since the RB is drastically reduced, the Fmax is dramatically improved. That's why you can achieve even higher Fmax than Ft. This is typical for silicon germanium HBT. Okay? 이해했죠? Okay. So this is a quantitative expression. So there exists a chroma factor, which is just expression intrinsic impurity. I mean intrinsic free carrier in terms of which is inversely proportional to the energy band gap. Okay, so owing to the energy band gap difference, right? So we have a high chroma factor. Okay, high chroma factor. So because of this is high, even we implant this high compensate this high. So we still can get beta much higher than that of BJT. Okay, that's what magic happens. Okay, so the base resistance RB is reduced because RB is just what? This is a sigma and area and length, right? So this length is actually this length is a base. This is actually inverse. Okay, this is actually inverse. So this is a sigma. Okay, so if you increase the Na, then RB is reduced quite a lot. Okay. Okay, let's take a look at the state of art silicon germanium HBT performance. So for certain HBT, I think this is a G2 IHP, 130 nano G2. If no, this is IHP. This is IHP G2. This must be IHP G2, and this is new one. Anyway, for this new one, FT higher than 500, Fmax higher than 700. This is a gigantic achievement, which is even comparable to indium phosphide, HEMT. Okay, HEMT, HEMT. Okay. So this is a typical. This is a silicon SG 13G2, which is from IHP. Okay, this is a real, cross-sectional view. Okay, so this silicon germanium BJT provide CMOS process as well, and whose gate length is 130 nano. This is not that bad. Okay. And as can be seen here, right? Key parasitics are RB, RC, and CCS. Okay. Also, yeah, CCS. Also, this is CMU. Okay. CMU is also very, very important, actually. Okay. CMU is a CMU is a CPC, right? Which is a CGD. Okay. This is a very important. So this is a typical BJT layout. Okay. So you guys must be very familiar with this one. So I'm gonna skip this. And also be noticed that IE is proportional to AE, right? Not AC or AB. Okay. This is nothing to do with this collector and base area. Okay. The IC collector current is directly proportional to emitter area, not other areas. Okay. So this is a the comparison of small signal parameters between BJT and MOS. Okay. So the most critical and important parameter is GM. Right? GM is very important. Okay. So basically, beta is what? Beta is IC divided by IB. Right? IC divided by IB. If you just write like this way, VT IB divided by VT, right? Right? You can write it like this way. This is a GM, and this is what? 1 over R pi, right? So which means that this is a GM R pi, core beta, okay? This is a BJT equation, the relation between GM R pi and beta. Here, RO is VA divided by IC. Here, VA is given by this. This is VA. And this is the slope of output current. This is a VTS. I mean VCS, VCE, right? VCE. So this slope is what? This slope S is I divided by VA approximately. Okay, that's why this is the slope is what? The slope is what? 1 over RO, right? Therefore, RO is I VA divided by IO. That's why you get this. Okay, those are just the definition. Okay, that's fine. For the CMOS, right? CMOS, the transconductance is given by this. So transconductance is directly proportional to VGS, right? VGS. This is very important. And also directly proportional to aspect ratio. Okay? And if you see GM is also directly proportional to COX, you come to know that why foundry company are struggling to reduce the thickness of oxide, right? So if you reduce the thickness of oxide, right, then you can increase the COX, then you can improve GM. Okay, so in terms of circuit parameters, transconductance is also given by 2 ID divided by P over the voltage. When you control the device using ID, the current source of ID, right? Then GM is given by 2 ID divided by V over V. Okay, here V over V is square root of 2 ID mu COX double over L. Okay. So in this, model, RO is 1 over lambda ID, right? Here, lambda is actually the slope. If you draw ID and VDS curve is something like this. Something like this. Let's say this is lambda. So as I said before, RO is lambda multiplied by actually speaking, this is I0 1 plus lambda V drain source minus VD set. Okay, so if you take a derivative with respect to VDS, then this becomes I0 lambda, right? I0 lambda is what? 1 over RO, right? Therefore, RO is what? RO is 1 over lambda ID. Here, lambda is proportional to 1 over L because this considers a channel length modulation. Okay. For the most input impedance is just J omega CGS, 1 over J omega CGS, which is expressed like G pi. Okay, 1 over omega CGS. If you define G pi in this way, you can also use BJT relation, which is a beta equal GM R pi, right? In this case, beta equal GM multiplied by 1 over J omega CGS. Okay, this is the current gain at high frequency for MOSFET. Okay, right. So, as I said before, the governing equation of BJT is given by this. This is IS. Okay, so again, if you take a look at the BJT, the minority carrier distribution is this. Okay, the initial value of minority carrier is Ni square divided by Nb, base current, base charge density, impurity, base impurity, number of base impurity. And this is proportional to VPE minus VT. Okay, so we are considering delta. So this, right? And also, this is a function of minus x and WB, right? So exactly speak LB, right? So here x is what? WB, right? Since WB over LB is much smaller than 1, so this exponential minus LB divided by x is approximated by 1 minus 1 plus LB x, 1 minus LBx. Okay, so if you put this together, then this is modeled like you can also model in different way. So let's say this is 0. Carrier is this is N0, and what is the slope? Slope is WB. Okay, so slope is WB and N0, and this is X, right? And this is negative. Okay. So the initial value is what? initial value is n0. So n0. Okay, so therefore you can model like this way, right? So this is the same with this, right? If LB becomes double B, okay? Since X is much smaller than LB, and LB is approximated by WB because this is a reverse biased. So this is the same with this, okay? Same with this. Anyway, therefore you can model like this way: MB, NI scale, and exponential over VT, VBE minus 1, and 1 minus X WB, okay? So J diffusion is what? AE multiplied by J diffusion is IE, approximately IC, right? IC is given by what? AE and number of charge Q, right? Because J diffusion is what? Q, dN, and round X, round delta N. Delta N, right? This is a delta N as a function of X. So if you take an integration, if you take a derivative with respect to X, right? What you have is just Q, dN, and all of them, MB, NI scale, and the only thing left is WB1. And you have this exponential, VT, VBE minus 1, okay? So those are this, okay? That's what we got, all right? So BJT operation in active region, this is a very easy to understand. So for the BJT to operate in forward active region, right? You have a base emitter junction in forward and base collector junction in reverse, right? Here we assume it is a reverse up to VBC is a positive 0.4, which is actually forward. Since if VBC is more higher than 0.7 volt, current conducts through this. But if VBC is less than 0.4 volt, there is no current at all. So we consider this as a reverse bias. Okay. So based on this observation, you can easily define, define the acceptable voltage level at VCE or VCE. Okay. Here VCE is what? VCE is VCC minus ICRC, right? This VCE should be larger than, higher than VCB plus VBE, right? Here, VCB, the maximum VCB is minus 0.4 volt from this. Therefore, VCE equals VCC minus ICRC should be larger than VPE minus 0.4 volt. Okay? That's why you get this relation. Typically, VPE is 0.7 volt, therefore it is 0.3 volt. Okay? So you can just safely say that if VC is higher than 0.3 volt, then it is operating in forward activity. Make sense? However, if this is a 0.8, then this should be 0.4 volt. Okay, You guys understand? Right. So this is a large signal model. As I said before, if VCE is smaller than 0.3 volt, which means VBC is higher than 0.4 volt, it started to conduct between base and collector volt, right? Therefore, the current in IB through this diode is reduced. Since this is reduced, this IC is actually proportional to beta IB1. Since this is reduced, this output value is reduced. So real beta is what? V in IB IC, right? Therefore, your output collector current is smaller than beta IB. Okay. This is the case for the saturation. Okay. So again, we can define the slope of this from I0 divided by VA, which is also 1 over RO. Okay. Therefore, we define RO as VA divided by IO. Okay. Here, this is a VA. It is early voltage. This is a widely used, level 0 model, level 0 RF model. Okay. So as can be seen here, you neglect R mu between base and collector. Okay. You just neglect it because this is high enough. Okay. And also, RB is very, very important, which define the Fmax. And this defines resonance at collector. Okay. So here, omega t is Gm divided by C pi plus C mu. Why? Omega t is defined like this way. So this is if you neglect this is grounded. So the total current, total capacitor is this plus this capacitor. Or if you neglect this, C pi plus C mu is the total current. Okay. So IC divided by IB is beta, right? So this beta, this IB is what? This IB is actually shown to be like this. R pi and C pi and it's something like that. C mu C pi. Okay. If I provide VI, right, then the current over here, if I assume R pi is much higher than SC pi, 1 over SC pi, right? Especially this is true when S approaches omega t, right? So this is true. So in this case, this current IC pi is approximately IB, which is what? VI J omega VI divided by J omega VI. Okay, J omega VI is IC pi omega C VI, right? So the current is conducting this and this as well. So C total, right? So I P is approximately J omega C total VI, and I out is IC equal GM multiplied by VI, right? So you just divide this by this. So GM divided by J omega CT equal 1. This is bad, right? Therefore, omega is what? Omega is CT GM, okay? Which is C mu, C pi GM. That's why you define omega T like this way, okay? Let's talk about the industry standard model of the BJT. Different from the CMOS. CMOS has a very, very good model, right? Which is a BSIM4 model, right? I'm gonna talk about this later. However, when it comes to silicon germanium HBT or BJT, there are two mainstream. One is a high-cum model, the other is a max-trend model, okay? But most RF, process, the PDK for the RF process utilize this high-cum model, okay? And both high-cum and max-trend are based on the, SPICE 군멜품 model. SPICE 군멜품 model. Okay, this is the first large signal model of BJT, which is briefly studied in your undergraduate class, right? So this is the comparison table. This is a SPICE 군멜품. This is a high-cum. This is a max-trend. Okay, we don't use a VBIC because if you take a look at this, right? Take a look at this comparison table, as can be seen here. You come to see why high-cum model is widely used, because this considers the most secondary effect. Even parameters are smaller than VBCI. Okay, that's why. Especially non-causative effect is quite important for RF modeling. Okay, that's why we use high. Okay, we also need to consider the substrate leakage and base emitter breakdown for power amplifier design and for noise model. That's why we use high-cum. Okay. However, high-cum does not, consider the current dependent base to collect the depletion curve, which is one of the nonlinearity factor in power amplifier design. Right? This will induce AM to PM AM to PM distortion. Therefore, you have to be very careful when you design power amplifier. The resulting AM to PM simulation is not actually correct. Okay, you have to be very careful. Okay, so this is a typical CMOS process. As I said before, the thickness is around 6. Okay, and top metal layer thickness is 1.8 to 3 micron. Okay, especially when you design passive device, so we have to consider metal conductivity, distance to substrate, because due to the lossy substrate and substrate conductivity as well. Typically, substrate conductivity is around 10 Siemens per meter, right, per centimeter. This is a typical for CMOS process. Why is this such a conductive? Why is the substrate of CMOS such a conductive? 왜 그래? 왜 CMOS 이렇게 conductive? 이거 conductive 안 하게 하면 되잖아. 왜 이렇게? 응? 누가 대답 좀 해봐요. 나 혼자 떠드냐 지금? 응? 내 혼자 떠들어? 수녀가 뭐 때문에 그래? 왜 컨덕티비티를 이렇게 짧게 만들어? 이제부터 내가 설명하고
인덱스
스킨뎁 아니 서브스트레이트 컨덕티비티 이야기하는데 왜 스킨뎁스인데 인터뷰한다고 생각하고 내가 이야기하는 거는 얘들아 나의 제자들아 내가 이야기하는 건 비서브스트레이트의 컨덕티비티를 이야기하는 거야. 왜 이렇게 작게 가져가? 이게 적으면 러시아잖아. 그치? 예를 들어서 여기가 서브스트레이트가 있는데 여기에 이렇게 인덕터를 만들거나 혹은 여기에 캐피스터가 있으면 스트레이 캐피스터 때문에 여기에 스트레이 캐피스터 있어갖고 서브스트레이트 러시안 서브스트레이트 이게 저항이잖아. 둘 다 안 좋잖아. 둘 다. RF 특성은 다 안 좋아. 이게 Q가 낮아지거든. 근데 왜 시그마를 이렇게 낮게 만드냐고. 왜 이렇게 낮게 만드냐. 뭐 때문에 그래? 레치업 때문에 그렇잖아. 레치업. 레치업. 알겠지? 이게 서브스트레이트가 기생 BJT의 베이스처럼 작동해. 그래서 서브스트레이트를 저걸 안 하면 임플란테이션을 이렇게 안 하면 베타가 커진단 말이에요. 그래서 레치업 될 가능성이 커져. 레치업을 줄이려면 베타를 줄여야 되잖아. 기생 BJT. 그래서 여기다가 어쩔 수 없이 이렇게 하이 컨덕티브로 서브스트레이트를 만드는 거예요. 됐지? 디테일한 건 찾아봐. 네. Okay, so this is the comparison of back end of the line between BiCMOS, the old, new one and old one. This is actually ST130 nano BiCMOS silicon germanium. Oh, this I don't know, but this is almost comparable to CMOS. Okay, CMOS. Okay. So as can be seen, right, the thickness is much thinner for CMOS, and the UTM also is a high thicker for silicon germanium process. So unfortunately, more metal usually means thinner dielectrics. So that's why as a processor node improves, right? As a scaling goes, right? The thickness becomes smaller and smaller and smaller. Okay. Also, redistribution layer or allocate layer, right? This allocate redistribution layers is now commonly available, right? But I always emphasize that whenever you use allocate, you have to be very careful. First, the allocate does not if you implement a passive element in with allocate, the passive element is not exactly same with the one you draw in the layout. 알겠지? allocat을 쓰면 레이아웃으로 그린 거하고 달라, 여러분. 실제로 밑에 걸 그리면 다마신을 하기 때문에 진짜 내가 이렇게 전송솔로를 그리잖아. 그럼 진짜 이렇게 딱 만들어져. 이렇게 밑에 레이어 UTM이나 이런 걸로 쓰면 이렇게 딱 만들어진단 말이야. 이렇게 그런데 allocate 쓰잖아. allocate 쓰면 이렇게 안 돼. 이렇게 안 되고, 이게 이렇게 이 크로스 섹셔널 에리어를 보면 이게 이렇게 돼 있어. 이렇게 돼 있어. 위는 다마신 안 하거든. 그래갖고 실제로 여러분들이 HFSS 갖고 크로스 섹셔널 이렇게 모델링 하냐? 안 하잖아. 그지? 안 하니까 뭐가 차이가 나냐면 Q가 차이가 많이 나. 높은 주파수에서 특히 Q가 차이가 많이 나. 왜냐면 서페이스 러프니스가 Q를 결정해. 주파수가 높아져. 이게 이제 HFSS로 알로캡으로 디자인하는 게 제대로 모델링이 안 된다는 문제가 있고, 두 번째 문제는 이 메탈은 알루미늄이라고. 알루미늄. 얘는 컨덕티비티가 대략 3 곱하기 10의 7성이야. 지멘스 퍼미터. 그러니까 어떤 문제가 있어? 보통 코퍼는 5.8 곱하기 10의 7성인데 우리가 사용하는 얼로이는, 코퍼 얼로이는 대강 그래도 한 5에서 4.5 정도 돼. 10의 7성이라. 훨씬 적잖아. 그러니까 Q가 또 떨어져. 알겠지? 그래서 whenever you design any transformer or any inductor using allocate, you guys need to be very, very careful. That's why I don't recommend you guys to use allocate when you implement transformer based architecture at millimeter wave reason. Okay? Have to be very careful. 이건 사람들 잘 몰라. 그리면 그리는 대로 나오는 거지. 알겠지? 자, substrate conductivity. That's what I already mentioned, right? So substrate conductivity is very important. Okay, so the current injection into the substrate through the displacement current, right, should be shielded or controlled through careful placement of substrate taps. Okay, what it means is that you should not make let's say this is a substrate. Okay, let's say this is a straight cap. For example, let's say this is a structure, and this is a main structure, and there exists a straight cap, and this is a very lossy substrate. This capacitor, okay, let's say this is structure. I don't want this straight cap, but unfortunately, it exists, and this will, induce lots of loss. Okay, how can I avoid this loss? You just place, tap, substrate tap over here. Okay, then this capacitor is not formed like this way, but goes through this way. Okay, this path is not shown. That's what I mean. You have to use a substrate tap at proper position. Okay. Also, the eddy current is an issue, right? Since this is a lossy, the eddy current will induce loss of loss if the substrate is conducted, right? So most of technology utilize relatively, resistive substrate, but it's not such a, not such a large. Right? This is a 10 ohm centimeter. ohm centimeter. Resistivity wise, right? Resistivity wise. Okay. So resistivity is inversely proportional to 1 over sigma, which means this is what is that? 10, 1 over 10, right? 1 over 10, and 아닌데 10 Siemens 정도가 맞는데. 자, 이게 지금 10 Siemens per centimeter. 그거 맞을 거야. 그러면 0.15 플러스 0.15 cm인데 이게 만약에 10이라면 0.01 Siemens cm가 되죠. 그치? 그러면 이게 0.01분의 1. 0.1이지, 0.1. 0.1분의 1 하면 10이지. 야, 이상. 야. 누가 지금 HFSS 가지고 있는 사람 있냐? 지금 열어놓은 사람 있어? 우리 저기, 서브스트레이트 모델링 한 거에서 컨덕티비티 얼마나 좋아하는 거? 나도 갑자기 깔린다, 이거. 어? 갑자기. 한번 봐볼래, 누가?
네, 확인해 보겠습니다.
민균이냐?
네, 맞습니다.
그래. 확인해봐봐.
컨덕티비티 10 지멘스 퍼 미터.
맞지? 퍼미터지, 퍼미터.
네, 맞습니다.
그래서 10 Gmen's per meter. 그래. Gmen's per meter. 자, 그러면은 만나보자. 10 Gmen's per meter면 10 Gmen's per meter면 얼마야? 센티미터에 100cm지. 그지? 그러면 Gmen's per centimeter로 따지면 얼마야 이게? 0.1 Gmen's per centimeter. 그지? 센티미터로 따지면 per centimeter당 0.1이잖아. 그지?
네, 맞습니다.
0.1 Gmen's per centimeter는 얼마? 얼마? 0.1분의 1이니까 10옴. 10옴. 여보세요? 예. 맞아요. 예. 제가 제가 지금 수업 중인데 뭐 대학원 수업이라 잠깐 아니요 괜찮아요. 저도 워낙 일하기가 너무 힘들어서 요거 해결해야 될 것 같아요. 예. 그러니까 이게 지금 어떻게 돼 있냐면 본래 IP 개방을 해주시잖아요. 그죠? 그래서 제가 기억이 나요. 정 선생님한테 부탁해서 지금 그 집에서 잘 쓰고 있어요. 네, 그거 아주 좋은데 제가 어떻게 하냐면 연구실에서 제 컴퓨터가 맥 컴퓨터예요. 그래서 맥 컴퓨터하고 제 PC하고 이제 맥 컴퓨터에서는 안 되는 게 많잖아요. 그래서 이제 PC로 연결을 해가지고 맥에서 그냥 PC를 보는 거예요. 리모트 데스크탑. 예. 그래서 지금까지 잘 썼는데 최근에 연결이 안 돼. 그래서 제가 이제 다른 선생님하고 이야기를 했는데 다른 선생님 이야기는 아마 이게 내부에 이제 내부 IP가 있잖아요. 뭐 192.168.5 해가지고 있는데 그 사설 IP로 하면 될 거다 해가지고 네 알겠습니다 하고 끊고 제가 수업 끝나고 했는데 안 돼요. 그래서 아마 생각에 아마 폴리시를 좀 엄격하게 하신 것 같아요 지금. 그래. 예, 예. 아 그래요? 아 그럼 내부에서 내부는 뭐 없나요? 오 근데 왜 갑자기 안 될까요? 맞아요, 맞아요. 예, 예. 근데 제가 지금 하고 있는 거는 사실은 이게 사설 IP가 아니고 그냥 옛날 우리 지금 쓰고 있는 그 210 주소 있잖아요. 210, 203. 그걸로 그냥 써가지고 연결을 했었어요. 그게 됐거든요. 그러니까 외부로 갔다가 다시 들어오는 거예요. 아, 그렇지. 그렇다면 집에서도 안 돼야 되는데, 집에서는 잘 사용하고 있거든요, 지금. 예, 예. 그러니까 이게 재밌는 게 뭐냐면, 내부망이잖아요. 근데 이제 예전에 사용했던 거는 A라는 내부망에서 B라는 내부망으로 내부망을 거쳐서 간 게 아니고, 외부망으로 나가서 다시 들어오는 거잖아요. 그렇게 되다 보니까 아마 여기서 보이는 IP가 그냥 폐쇄가 되는 것 같아요. 아, 제가 이제 포트를 이제 하나 열었고요. 이제 뭐 저기 4천 얼마로 되는 거 그걸 열어놨고 거기에서 이제 이렇게 해가지고 열면 내부에서 이제 그 PC하고 관련된 사설 그 뭐냐 저기 IP로 들어가도록 해놨거든요. 근데 이제 그게 한 가지 하나만 선택될 수 있어서 제가 그래서 어떻게 했냐면 맥북에서는 그냥 이거는 네이버 IP 안 쓰고 외부로 그냥 나갔다가 이렇게 들어오는 걸로 잘 썼었어요. 왜냐면 어차피 이게 그때 됐던 이유가 저는 생각에 이게 어차피 210 같은 내부망이니까 열어놨다 이렇게 생각을 했었거든요. 아, 예, 그러니까요. 그러면 선생님, 혹시 제 지금 학교 IP에서 접근하는 거를 열어주실 수 있나요? 혹시? 그게 되나요? 예. 그래요. 그러면 혹시 제가 1094-203-188인데 이거를 열 수, 뭐 이렇게 주시는 그런 개념은 없나요? 우리 집에 건 열어주셨잖아요. 그죠? 예, 예, 예. 예. 예, 그거는 잘 열려 있어요. 근데 1094-203-188에서 2094-203-188도 이상하잖아요. 그죠? 맞아요. 맞아요. 예, 내부망 IP죠. 예, 맞아요. 예, 예, 예. 나오죠. 예. 아, 이거를 어떻게 해야 될까요? 그게 없으면 갑자기 안 되니까 좀 답답하네요, 진짜. 그렇죠. 그렇죠. 예. 그렇죠. 아, 예, 예, 예. 예, 예, 예. 예. 예, 예. 예, 뭐, 그럼 뭐, 제가 뭐, 그냥 다른 방법을 찾아야죠. 그러면. 예, 예, 예. 아, 이거 참, 이거 뭐, 일이 안 되니까. 왜냐면 제가, 그래서, 이게 멀티로 지금 모니터를 그런 식으로 쓰거든요. 근데 이게 지금 그, 뭐라거나, 구글 리모트로 하면, 멀티 모니터가 또 안 되거든요. 예, 그러니까 이거 너무 힘든 거예요, 그러니까. 방문해 주시면 제가 신공학관 8115고요. 예, 그리고 제가 저기 금요일 날 9시부터 10시 반, 그 다음에 1시부터 2시 반, 4시부터 5시 사이에 있습니다. 예, 예, 나머지 수업 있습니다. 핸드폰으로 좀 부탁드릴게요. 제가 출장도 좀 많아서 010-8686-7411입니다. 예, 예, 예. 아유, 예, 감사합니다. 예, 감사합니다. 예. 그러면 진짜 미치겠다. 야, 어디까지 했냐, 내가? 잠깐. 들리냐? 여러분들?
네,
여보세요?
들립니다.
아,
네.
미안하다. 하는데. 오케이. so, 이게 맞아, 그지? 10 G면서 per 미터는, 10 옴 센티미터야. 이게 센티미터가 아니야. G면서 per 센티미터가 아니야. 아까 이야기한 거. So, 이건 또 미터로 해놨네. 10 G면서 per 미터로 해놨네. 어? 10 G면서 per 센, 10
아, 네,
G면서,
네, 그거
맞아.
계산, 네,
어, 오케이.
하셨습니다.
오케이. Alright. So, okay. So there are another issue. Okay. So this is one issue. Okay. We have a relatively low, resistivity. Actually, this is low, not high. Okay. So since this has a low resistivity, it has a high loss with the eddy current and with the, electric field, coupling. Okay. Second issue is related to, you know, automated, you know, well formation. Okay, so basically, many process has a, surface with a well. If a well is automatically placed, this well has a even lower resistivity. Okay, this means high conductivity. This means high loss. Okay, because of this reason, whenever we make an inductor or transmission line, we use exclude layer, right? Exclude layer. Okay, this is a well block. Okay, so the easy peasy way for different types of process the easy peasy way to find the the well block for different types of process is just to investigate automatically generated inductors. Okay, you just pattern the inductor layers and take a look at each layers. Then you can easily see what is defined as well block. Make sense? 알겠지? 여러분들 이거 자동으로 인덕터 그려주는 그런 거 하나 인덕터 만들어 가지고 이걸 패턴에 해가지고 각각 보면 뭐가 익스플로드 레인인지 알 수 있어 쉽게. Okay. This is the structure and symbol of MOSFET. So this is effective length, gate length, and this is effective gate length, drawn gate length. So the L effective is always smaller than the real drawn in the gate length. Okay, because of side diffuse. Okay.
교수님 화면이 아직 19페이지
공유가 정리돼 있어? 왜
그런 것 같습니다.
공유가 안 되지? Okay. Alright. So can you guys see?
네, 보입니다.
Okay. Therefore, considering there exists a 10% of diffusion length, okay, and considering oxide thickness is 15 angstrom, right? So typical, considering the thickness of oxide is 15 angstrom, and angstrom, the LD is about 10% of L drone. Okay. For example, let's say this is a 45 nanometer in drone. Then effectively this is around 40 nanometer. Okay, because each side is just 4 and 4, 2 and 2. This is 10%, right? 10%. Okay, so this is actually this LD is this is a little bit exaggerated. 이거가 조금 안 맞는데 그냥 대강 이렇다고 그냥 아세요. 이거는 버클리 자료인데 어쨌든 typical value of 40 nanometer CMOS has a LD equal to 10% of L3. Okay, just for your information. Also, S terminal provide a charge carrier and D terminal collects them. Okay, this S is a source because it provides a charge, and D is a drain which collects the charge, right? Carrier, right? So so eventually you can see this symbol. So we notice there exists the body, right? This is the MOSFET region of operation, different from the BJT. This triode region is relatively wide compared with the applied BDS. Okay, this is very wide. So considering the BJT has a relatively narrow region of operation for the saturation, right? This is a narrow compared with the VCE, right? So we don't use it here for BJT. However, for CMOS, this is a very important region of operation, especially for variable resistor, right? Variable resistor. Okay, we use this region. Okay, so how can we differentiate between triode and saturation? if there exists a channel between gate and drain, there exists a channel between gate and drain here, right? Yeah, like this. Then this is triode. If there exists, there is no channel at all at gate between gate and drain, this is a saturation. Okay, we need to operate MOS in saturation, right? So we have a very important relation based on this. What is this? VDS. What is this? VGS. What is this? VGT, right? Which is a minus VDG. Okay. So VDS equals VDG plus VK source, which is a VK source minus VGD, right? If VGD is a V threshold, it forms channel at this point. So we can derive the criteria. VD set equals VGS minus VGD, which is a V threshold. Okay. So if V drain source is smaller than VD set, which means this gate drain voltage is higher than threshold voltage. That means it is in triode. Okay, very easy. So in triode, this ID is a function of VDS. This is important. A function of VDS. Okay. However, in saturation, since there is no channel exists between gate and drain, right? There is no channel exists between gate and drain, right? So if voltage, applied voltage VDS is higher than VD set, right? What happened? The effective channel length is slightly reduced because depletion region is increased, right? Since the depletion region is increased, it does not, contribute to form more channel, more charge. Charge is not increased. Charge is not increased by increasing VDS. Therefore, once VDS is larger than VD set, then current is constant. Okay? This is actually controlled only by VGS. Okay, so IE is only a function of VGS, not VDS. Therefore, this is a voltage controlled current source. Okay, that's why we call this as a voltage controlled current source. Okay, so in understanding MOSFET operation, understanding of threshold voltage is very, very important. Okay, so this is so clear that V threshold voltage is the voltage which induce channel underneath of the oxide, right, at the surface of the substrate, right? So the definition of channel formation is when the induced channel current charge density equals to the channel dopant concentration. Then we say it is a strong inversion. Okay. So for the P substrate, it is doped by Na. Therefore, the potential at the surface of a P substrate body is given by this equation. Okay, so this is this potential. since the channel is inversed, this amount is exactly the same with this amount. So the total potential at the surface becomes 2 pi p. Okay, right. So in order for us to provide a channel, we also have to provide this amount of potential at the surface. So this is a prep and voltage which make this this prep. Okay, this prep. So we need to provide a negative voltage, negative prep and voltage, or MOS, because we have to apply voltage heading, apply the voltage to this wall, this wall, which means this is negative. V prep and voltage is negative, or MOS. Okay, this is negative. And also there exists a potential at the surface, and there exists another potential caused by the depletion at the surface. So this is a depletion, depleted charge density divided by Cox, okay, which is effective potential. So apply the built-in potential is 2 pi b at the surface. So the XD multiplied by what is that? The Na multiplied by Q is a Q differential, Q depleted. Here XD is what? XD is 2 epsilon silicon and divided by Q and Na1, right? And multiply by 2 pi b. This, okay? So you put over here, this is XD, then you get this. That's why you get this very widely known, threshold voltage relation. You notice that VFB is negative and threshold voltage is positive for MOS. Okay. So since we typically use this gate capacitor as a load. This is a load. Right? Let's say this is a inverter, and this is the gate capacitor at the gate capacitor of next stage. So what you see is this. So we model this as like this way, right? So we are interested in total charge Q, Cox multiplied by V, right? This Q. How can we, understand the stored charge Q in terms of the charge at the input? Okay, so let's say this is an insulator. If you apply charge Q, right? Charge QG at the gate, right? Then what happens is that, let's say this is positive. Then it becomes a negative because of polarization. And this becomes a positive, right? So the induced charge is negative, which is N channel for the MOS, right? So the surface charge density, let's say it is QS, then QG is naturally minus QS. Okay, that's what it means. So since the QS is negative, and we are not interested in QS, but we are interested in QG because this is a stored capacitor, a stored charge at the input of the gate. Okay, so we can draw charge in this way. So in depletion, right? For example, in depletion, the carrier is depleted. This is a p substrate, which means the bounded the bonded charge must be charge must be negative, right? Negative in depletion, right? This is a fixed charge, right? So this is a negative, which means if you consider gate charge QG, it is positive. It is positive. Okay, that's why this is positive. Inversion is the same. When it is inverted, the surface charge density, the charge density around the surface is negative, which means the gate charge is positive, right? It's something like this, right? Because Q is a function of square root of 2Q epsilon silicon and 2 pi b, right? And Na, right? This is this charge Q. Okay, so as VGB increase, VGB, right? So as a VGB increase, right? This is proportional to square root of VGB. So it's looking like this. Once inversion happens, then the charge is directly proportional to VGB minus V threshold, like this. However, for the accumulation, when negative charge is applied, then negative charge, positive charge, negative charge, positive charge. The hole in the P substrate is gathered over here and accumulated. Therefore, in terms of gate, accumulated charge is looking like negative. That's why it's looking like this. The PMOS is opposite, right? PMOS is opposite. This is accumulation, looking positive, depletion negative, inversion negative. Okay. So this is the capacitor. We typically use the capacitor shown at the inversion. So you can just model like this way. This is a capacitor in the oxide capacitor, and this is a capacitor in the channel, and this is a COX. Right? So when there happens, this is a substrate depletion. Okay. So if channel is formed, right? You don't see depletion cap. You only see COX cap, right? So however, when it is operating in the depletion region, total C is just a COX, C dip, COX plus a C dip, which is smaller than COX. Okay, that's why it's looking like this. Okay. In accumulation, what you can see is this P substrate, right? So this is the same with the capacitor over here. 그래서 여러분들이 언제 뭐를 쓰냐? 여러분들 모스캡 쓸 때 어느 영역을 쓰냐 이가. 어? 엠모스 쓰잖아 우리 지금, 그지? 엠모스를 모스캡으로 쓴다고. 엠모스를 모스캡으로 쓰면 어떻게 돼? 인버전이라고. 인버전. 어? 인버전에서 인버전 영역에서 쓰는 거야. 문제가 뭐야? 이 VDD가 모스캡을 썼어요, 여러분들이. 이걸 이해를 하고 있어야 돼. 이걸 보고. 모스캡을 썼어. 이 VDD가 스레시홀드 볼티지보다 더 낮아져. 어떻게 돼? 어떻게 돼?
콜리전.
디플리션 영역으로 가잖아. 그래갖고 C 바이패스가 확 작아져. 또 하나 문제가 있어. 여기에서 시그널이 가면, 시그널이 이게 왔다 갔다 가면, 이게, 그러니까 여러분들이 모스캡은 절대로 로드로 쓰면 안 돼. 알았지? 로드로 쓰잖아? 그럼 스윙이 들어가잖아? 그러면 이게 디플리션 영역에 있다가, 인버전 영역에 있다가 왔다리 갔다리 한다고. 이걸로 인해서 시그널이 완전 디스토션 돼. 그래서 AM to PM 디스토션이 난다고. 절대로 never ever try to put MOSFET piston as the load. Okay? Only use MOSFET just directly connected to VDD, which is operating at this region. Okay? 알겠지? 야, 씨, 너무 끝도 없네. 끝도 없어. 가만있어. 아이씨. 그냥 뭐 자세하게. 너 다 아는 내용 아니야, 이거 다? 다 아는 내용 내 또 하는 거 아니야? 내 입만 아프지? 다 알지? 근데 희한한 게 시험을 치면 몰라. 보면. 그러니까 내가 고민이 있는 거야, 이게. Okay. Let's take a look at capacitor. Okay, capacitor of the MOSFET. So basically different from the BJT. For the BJT, right, as can be, seen before, you have a gate, you have a C pi, right, which is a C base to emitter. Okay, C base to emitter, and you have a C mu, which is a C base to collector. You have a emitter to substrate. You have a collector to substrate. You have a collector to substrate. Collector to substrate. How about emitter to substrate? Do you have? Typically, we don't have this, right? Why? If you take a look at the structure of BJT, right? This is emitter, and this is a base, right? This is a N, this is a P, and this is N. This is collector, okay? Collector and base and emitter. So definitely this must be C pi. Definitely this must be C mu. Definitely this must be CS. How about CE? Can this emitter C substrate? 볼 수 있어. 이렇게 볼 수 있어.
안 보입니다.
안 보여. 그래서 이거 없어. 이거. 알겠지?
네.
Different from this BJT, the MOSFET has a CGS, CGD, CDS, CSS, CSP, we typically say CSP, CGD, okay? So this is a bulk. Okay, so we have a, as you can see here, right? As you can see here, MOSFET is looking like this. So this is a CGS, this is CGD, this is a CDB, this is a CSB, right? So we have a four capacitors. Okay, so we have this, and also sometimes we describe CGB as well. Okay, but this is not that important. Okay, not that important. So as can be seen, CGS is typically caused by the fringing capacitor. This is an overlap capacitor between gate and source, because there exists let's say this is a gate width. At the edge line, there exists a fringing stray capacitor, fringing field, which cause COL. Okay, same for CGD as well. Fringing stray capacitor cause CGD. Okay, so CGD, this is an overlap. In modern technology, right, this overlap is mostly this is straight cap. Okay, so I just express this straight cap as a COL. Okay, so CG, let's just skip this first, because this is not that important. How about CSB? CSB is a source to bulk, right? This is definitely junction cap, right? This is junction cap. So we just describe it, CJSB, okay? CDB is also junction cap, okay? So that's how it goes. In the weekly inversion, right? In the weekly inversion, there is no, definite, capacitor between these two. Okay, so since there is no channel at all, right? We neglect. If there happens a strong inversion over here, this C oxide is clearly seen, right? So this capacitor is just a COX double L, right? Because this is symmetric at at the for source and drain, right? So CGD becomes this divided by half. Also, CGS is the same, right? So like this, and plus straight. Okay, this is a strong inversion case, but strong inversion doesn't necessarily mean this is in saturation, right? Strong inversion in linear is like this way, which means it is in triode, right? It is evenly distributed. Okay, that's why we have this. Since there exists conduction layer, so we don't see any gate to body capacitance, so it becomes 0. Okay? There is no conducting capacitor at all, then you have these two, CGC and CCB, something like this one. That's why we express it like this. Okay, this is just a CGC, CCB, CGC and CCB. Okay. How about CSB? We also have a junction in half. Okay. So this is a junction in half, okay. Also, you know, there is a actually this is a serious side. This is actually this is junction. This is channel to body. Okay. Okay. This is channel to body. Channel to body capacitor. And we divide it by half. Okay. Then channel to body. And this is junction at source. Junction at drain. Okay. Which is an intrinsic junction cap. Okay. That's what it is. For the strong inversion, right? Strong inversion with the saturation. The channel is looking like this. Channel is looking like this. So the effectively, the channel is CGC multiplied by 2/3 due to the distribution effect. Okay? Distribution effect. And also there exists the overlap cap, COL. Okay? This is a CGS. CGS is shown. Since there is no channel at all at this point, so we have a COL only at gate drain. Okay, and we also neglect CGB and also CSB, like this way. This channel to bulk capacitor is two-thirds of a channel capacitor. Channel to bulk capacitor is at source, and we don't have any channel to bulk capacitor at the drain. Okay, so most important part is this CGS and also CGD. We don't care on this much. MOSFET also work as a voltage control resistor. Okay, so R on resistor is a resistivity multiplied by L, T inversion, thickness of inversion layer, and width. Right? So as we observed before, resistivity is just conductivity. Conductivity is Q and U, right? This is a resistivity. So also, area is a T inversion and width, and length is L. That's why we get this. Okay. So we already derived the relation between this and this one. That's why we got channel resistor is a function of applied gate voltage, like this. Okay. So MOSFET with a VDS equal to almost 0, then MOSFET is working as a variable resistor. This is a source and this is drain. Okay. MOSFET transconductance is defined like this way, as we observed. For short channel MOS, GM is V saturation multiplied by W Cox. Okay. This is it. Okay. Let's take a look. let's skip this. We already investigated this. Okay. So for the output resistor line, actually we just modeled it. This is a slope. This is a slope of this line. This is number. But in real MOSFET, this is not that simple. Okay. As can be seen here, this is a RO. Right? Depending on the drain source voltage, right? RO ranges from, let's say, 100 ohm to 8 kilo ohm, which is very, very different, really different, right? Depending on VDS. Okay. So it is hopeless to model RO with a simplification. Okay. There are several, secondary effects involved. The first one is channel length modulation, as we observed. Second one is a drain-induced barrier lowering effect, Dibble effect, right? Which means when applied, the drain source voltage is getting higher. Threshold voltage is getting lower. Okay, threshold voltage is getting lower, which means there exists increased drain source current as VDS increases. Okay, that's Dibble effect. So you look at this, right? You just this region is drain-induced barrier load region. This is channel length modulation region, which is just modeled in lambda ID, right? And there is another secondary effect which is called as substrate current-induced body effect, SCB effect, right? As saturation region, but with a high VDS. In typical operation, we don't operate MOSFET in this region. Okay. We don't operate. Okay. So mostly we operate between this and this. Channel length modulation and T1. And as can be seen here, right, this slope is almost the same with this slope. Of course, clearly speak, V out slightly increase as it goes to T1. So this is the setup for extracting AV equals GMRO, which is intrinsic gain. Okay, this intrinsic gain is actually more useful than RO value. Okay, this represents the maximum attainable gain from a transistor. Okay, for example, this is a GMRO value. Okay, as VDS increases, GMRO is in the range of SOLT, right? In the range of SOLT. Okay. And how can we extract the GMRO? Definitely, GMRO is a function of ID. Right? You notice that this is a function of ID. So you have to control ID, right? So how can you control ID? In order for us to control ID, we have to control VGS. How can you control VGS? We have to use this configuration. So we set ID using ideal current source. Okay? And this ideal current source is connected to drain source of drain of this DOT. And we also provide VDS over here, because this is ideal current. We don't know about this voltage, right? How can we define this VDS? Right? That's the question. Because this is ideal current source. This node voltage can be anything. So how can you solve? How can you resolve this? If I connect directly this to here, then this is diode connected device. It does not provide any high impedance, right? It does not provide any high impedance because R out is 1 over GM, right? So it always AV is always 1 if you directly connect this to this. So how can you do that? Instead of connecting over here, we use ideal feedback comparison, comparison amplifier, error amplifier. This is called error amplifier. Since the gain of this error amplifier is relatively large, which is around 100. Okay? If this value is bigger than 100, then it takes more time to make it converged. But anyway, what it happened is that this just drive this VDS, this value close to this value. Okay. Why is that? Because it provides more current. If there exists error, right? It provides more current, right? More current, but current is fixed, right? So this is automatically tracks this to make this delta voltage exist. Doesn't exist. Right? Makes sense? The reasoning is this, right? If there exists delta V in, then this delta V in make a delta ID at the output. But this is always 0 because we use a current source. That means delta V in is always 0. In order for this to be 0, this V in plus should be always V in minus. Otherwise, it will not converge. Okay? So this is called the error amplifier, and by using this, you can drive this to this voltage. Okay? Now let's talk about body effect. Okay? Body effect is just something like this. If you apply reverse bias to P substrate, which means that this has to be negative, right? Compared with more negative. This has to be more negative compared with the substrate. Compared with the source. Okay. If it is biased with a negative, reverse biased with a biased in reverse mode. So this is negative, and this negative will induce, hole to here. equal to here. Therefore, the fixed charge is increased, which means the depletion is increased. Since the depletion is increased, the threshold is what? Prep band plus 2FB plus Q depletion divided by COX, right? Plus this, right? This, right? So Q depletion, this is the problem, right? Q depletion is increased, which means the V threshold is increased. Okay? Therefore, V threshold is a function of V body source. Okay? You notice that this V body source is always less than G, which means that this is reverse biased. Okay? So, using the previous relation, threshold voltage can be expressed in terms of intrinsic threshold voltage plus source body voltage, right? Okay, easy, right? Here, gamma is a process parameter. We don't care on that. So, as we observed before, threshold voltage is flat band voltage plus 2, surface potential plus Q depletion divided by COX, right? This Q depletion is proportional to square root of VSB, right? So it's looking like this. So we want to use V threshold 0 with a VSB equal to 0 here. And we included the effect of V source body like this way. So eventually you have a very important equation for threshold voltage. Okay. Therefore, in order to reduce the body effect, we have to reduce this gamma. Right? Gamma is this. How can we reduce this gamma? We need to increase the COX, right? Or decrease NA, but this is a limitation considering the lecture, right? That's it. So, if you withdraw MOSFET, this is gate, this is body, this is source, and this drain. So this is gate 1. We consider body as gate 2. Okay? We consider body as gate 2. Therefore, as we define transconductance as a relation between ID and VGS, we also define V body transconductance as ID and VES. Okay? So from this relation, we can link between GMB and GM. Okay, here psi is around 0.2. Okay. Oh, this is not volt. Okay, 0.2. Okay, which means you have a two gate 1 and gate 2 for the MOSFET. If gate 1 has a transconductance of GM, gate 2 has a transconductance of 20% of GM. Okay, 20% of GM. So to eliminate the body effect, right? The easiest way is just connect this to source. Then VBS is physically 0. Therefore, there is no body effect. Okay. So to connect body to source, we need to use a triple layer device like this, right? So this is a body. in triple well device, this body is inside of the P well, not piece of straight like this. Okay. Therefore, you can easily connect this body to this source. It's fine. How about this? If I connect this to here, and let's say there exists a source resistor, then you are dead because your P sub can be positive, which make your substrate in forward biased. Therefore, your circuit as a whole will not work. 이 조심해야 돼. 그래서 MOSFET in off state. So if MOSFET gate source voltage is less than threshold voltage, right? In our previous model, right, if VGS is less than V threshold voltage, then there is no channel at all, because this is a total charge in the channel, right? So if VGS is VTH, there is no channel line. If VGS is less than VTH, there is no channel line. But this is not true. Okay. Even though there exists no channel between source and drain, we still have a BJT. Why? Because this is N, this is P, and this is N. Okay, which means NPN transistor, NPN BJT. Okay, so this is basically looking like this. Okay. So this gate is actually this, right? This is a base. So V base, applied voltage at base. V base is actually what? V base is V gate multiplied by C aux, C depletion, C aux plus C depletion, and this is a C aux. Okay. This is a body. Okay. So if I define this as 1 over eta, right? Then maybe 1 over eta인가? 1 over eta, then it is expressed like this, exponential, and Vt and Vb, right? Vb is Vgg multiplied by C aux plus, this is a 1 over eta, something like this. And eta is what? Eta is C aux plus C dip C aux, which is 1 plus C aux C dip. Okay, this is equation for the off state MOSFET in sub-threshold MOSFET. Okay, so as a conclusion, MOSFET is operating like a BJT if gate source voltage is less than threshold voltage. Okay. Let's talk about velocity saturation. In modern MOSFET, right, channel length is even less than 0.1 micrometer. Therefore, this lateral field E is very, very high, right? So as we observed, right, ID consists of channel charge multiplied by velocity, right? channel charge. Actually speaking, this is proportional to rho multiplied by velocity and area, W Tox, right? So this rho Tox is proportional to Cox VGS minus V threshold. And this velocity is, previously it was VGS minus V threshold divided by L. Now it is just a V set. It doesn't change depending on VGS. It doesn't change. It is fixed. Okay, which means ID is only proportional to VGS minus V threshold, not VGS minus V threshold scale. Okay, no. Hold on. Okay, therefore, in short channel device, I is just proportional to VGS minus V threshold, not proportional to scale. Okay, makes sense? Because velocity is already saturated, right? The velocity does not increase as electric field increases or as VDS increases. Okay, so ID is only a function of VGS minus V threshold. Okay. Also, therefore, because of this reason, right, ID is not function of 1 over L. Okay, because it is already saturated, not function of L, but function of W. Okay. Also, VD set saturation is very arbitrary, because if you take a look at this, where is saturated region? Where is saturated? It's changing smoothly. Which one is VD set? Okay, you understand what I'm saying? So this VD set is even smaller than V overdrive voltage. V overdrive voltage is defined as VGS minus V threshold, right? That's why it's called as overdrive voltage. Right? Overdrive, then threshold voltage. That's why it's called as overdrive voltage. So in short channel device, VD set is smaller than overdrive voltage. Okay? Also, channel length modulation is apparent, which means we see channel length modulation and we see Dibble effect. Base induced barrier lowering effect as well. So in analog device, this short channel effect is not that drastic, actually speaking. So you can easily model, the effect of mobility in this way. U equal 1 plus V overdrive E critical length, right? So by using this over here, you can, rewrite the equation like this way. But if you rearrange those lines, it is looking like this. Mu Cox double over L and overdrive voltage, right? And this is just what? ECL multiplied by V over and ECL plus V over, which is exactly something like this. V over and ECL, okay? So if ECL is smaller than V over, right? This is dominate. this dominates. So if this is the ECL, then it is only a function of V over the overdrive voltage. Okay? So you can still, include the effect of saturation, velocity saturation in current equation. Okay? Also, interestingly enough, right? This ECL is different depending on the process technology node. For example, 1.18 micrometer, right? ECL is 2.1 volt. This is relatively large. However, for 60 nanometer, ECL becomes 0.7 volt, which is relatively small. As process goes scale down, this ECL is smaller and smaller and smaller. Eventually, ID becomes just a W, COX, and VOV, and VSET. Okay? So this is a simple model. In digital circuit, right? Digital circuit, our operation is very drastic, changing from here to here, very drastic. So we definitely need to consider velocity saturation in digital circuit design. However, for the analog circuit design, actually, this is not that serious. Why? Because our VDS is typically small, around here, maybe, right? So if a VD set is V drain source is a V, so here, around here, right? This is not velocity saturated. This is saturated with a V gate source is small, and VDS is small. Okay. Okay. This is good information. So let's take a look at the technology trend in MOSFET. Okay. The short channel device suffer from reduced intrinsic transistor gain. GM-RO is reduced. Okay. Why? Because RO is proportional to 1 over L. Proportional to L. So L reduced, R reduced. Okay. GM, when it comes to GM, it's the same, right? GM is what? GM is W COX VSET, right? Or GM is mu COX double over L V over the right. So as a GM, as an inductor reduced, as a gate length reduced, RO reduced, but GM is almost fixed for short channel device. So this is always reduced. So as can be seen here, right? It reduced. Yeah, it reduced. But good thing is that, as I said before, if VDS is getting smaller and smaller, difference is not that big. Okay, that's why we still can design analog circuit with a scaled device. Okay, this V star is the reason of introducing V star is that, as we observed, right, we don't know where VD set exists. Definitely, we understand that VD set is even less than V over the high voltage. Okay, then where is a VD set? If you draw, it's something like this. Where is a VD set? Where is a VD set? This or this? How can you know? So we define VD set such a way that GM, which is extracted from the spice, is 2ID. This is our applied current, and V star. Okay, we define like this way. So V star is what? V star is 2ID divided by extracted transconductance. This is a V star. Okay. So using V star, let's design amplifier whose AV is 70 and unit frequency is 100 megahertz and CL is 5 picofarad. Okay, so AV0 is in order for AV0 is 70, right? We find L. We also know that L is 0.35 micrometer. We have to use the minimum gate length, right, to provide a higher gain, right? So this is a reasonable choice. Now, how can we define this, right? This is what? This is actually GM divided by CL, okay? This is 2 pi CL is 100 megahertz, okay? So from this, we understand the GM has to be this, right? So we require the transconductance, okay? Then we choose, this is arbitrary, but this is reasonable, okay? We choose the V star is 200 millivolt. Then V star is what? 2ID divided by GM, okay? So the required ID is what? GM V star divided by 2, okay? So we know GM, we know V star, so the ID is 314 micron, okay? Now how can we extract? How can we extract the value with a designated V star? Okay, that's how we get. Okay, so this is a 314 micron. We apply, right? So this is just a large capacitor to avoid any, issue. You just want to make a, AC ground, not to involve any AC action. So this is just a DC open, and this is a DC. We just capture this signal here, right? And we connect this and this as we do before, right? So this will provide required gate voltage over here. Gate voltage over here. Okay. So this gate voltage is providing this like a current meter, right? And this VDC is providing the voltage over here. Okay. So we apply all required, bias. So this is a log graph depending on VGS or VBE. This is what I already mentioned, right? So I will skip. Threshold voltage trade-off. So as I already mentioned, right, ID set is proportional to VDD minus V threshold. Eta is for the what is that? Square row device each two, or the velocity saturated device each one. Okay, so we just model like this one. as can be seen here, right? In order to reduce ID set, in order to increase ID set depending on V gate source, we need to reduce V threshold. If we reduce V threshold, the problem is leakage current is increased. So for low V threshold voltage, you know, the leakage current is very large, very high. Leakage current is large. For high threshold voltage, leakage current is very small. Difference is this amount in log scale. Okay. So if we reduce too much, right, then leakage current is too high. So HVT device is used for mobile application. MOBILE, mobile. BILE, mobile application. Low VT is a high performance. High performance device. Okay. HVT is a mobile application whose leakage current should be small enough. So this is a weak strong inversion of MOSFET as a function of GM over ID. This is a performance figure of merit for performance of analog circuit. 이건 뭐야 이게? 이게 일한 거고 이게 준 돈이야, 그지? 이게 일한 거고 이게 준 돈이야. 그래서 돈 적게 주고 일 많이 하면 성능이 좋은 디바이스야, 그지? 자 보면 제일 큰 게 뭐야? BJT야, BJT 아날로그 디바이스에서. 그 다음에 지금 이거는 스트롱 인버전이고 이거는 위크 인버전이야. 그래서 위크 인버전일 때는 아까 봤지만 에타로 스케일링 돼. 그치? 에타는 아까 1 플러스 C 옥스분의 C 디프리션이야. 그치? 이렇게 스케일링이 돼. 작아. 그렇지만 역시 뭐 이렇게 되고. 그 다음에 이제 스트롱 인버전이 되면 어떻게 돼? 이게 롱 채널 디바이스입니다. 그치? GMID는 EFVD 오버드라이브 같아. 그치? 그러니까 이렇게 ID가 증가할수록 이렇게 떨어져. 이렇게. 그치? 자, 됐죠? 그 다음에 이제, alright, so this is a graph. Graph of ID as a function of VGS. So when VGS is smaller than threshold voltage, it is a weak inversion. And if it is larger than threshold, it's a strong inversion. And at certain, VGS, then it becomes a velocity saturation. So this is a function of V over V square. This is a function of V over V, okay? Linear. So if you draw GM, it's looking like this. Okay. So typically we just calculate total GM in form of this. Right? GM is this GMK, right, and GM saturation. Okay, the smaller one dominates. Okay, that's what it means. Okay. As I said before, for the CMOS, we use standard model. We have a standard model. This is a Berkeley short channel IG FET, insulated gate, FET model. So you notice that this insulated gate is a true name of MOS because we don't use oxide, right? In modern technology, we don't use oxide. So we should not actually speak, we should not say MOS. Exactly speak, this is a insulated gate. Insulated gate FET. So IGFET is correct name. Okay. Anyway, BSIM means this. Okay. So the research group at Berkeley, exactly speak Chen-Ming Hu, okay. Professor Chen-Ming Hu's group just developed this. Okay. So this has been widely used all over the world. Okay. TSMC used this, Samsung used this, Intel used this. So PSIM4, there exists website. So you just check this website. They update model in free. Interesting, right? They update model in free. Okay, that's a Berkeley policy actually. FE, what is that? FinPad, right? FinPad was actually invented by Chen-Ming Hu's group. The originality is from Chen-Ming Hu's group, but Berkeley does not file any patent. That's why someone in our country filed the patent and made lots of money. Also became minister, right? I don't know who he is, but that's what it happened. Okay. So this is a small signal model. You notice that there exists, NQS effect, non-quasi static effect, delay, right? Delay tau, and RC. I remember omega tau. Omega tau is RIGS. Omega tau. This is omega tau. Okay. Omega tau. Okay. This is not NQS effect. Okay. So anyway, this RI is also also modeled as 1/5 GM. This is also NQS effect. Non-causative effect. Non-causative effect가 뭐냐면 기본적으로 채널이 인가되는 전압의 속도를 못 따라오는 거야. 그래갖고 딜레이가 생긴다 이 뜻이야. 알겠지? 스테이틱하다고 가정하고 우리가 이런 모델을 푸는데 스테이틱하지 않는다고. 그거가 뭘로 표현된다고? 이런 딜레이들은 다 저항으로 표현돼. 그래서 저항으로 표현돼. 그렇게 이해하면 돼. Okay, so let's take a look at each of them. So channel charging resistance. Okay, so this is the NQS parameter. Okay, so channel charge cannot instantaneously respond to the change in the gate source voltage line. So there should be delay, and delay is represented by the resistor. Okay, so we call this as an NQS resistor. Okay, so approximately this RI is 1/5 GM. Okay, this is a very important one. And also gate resistor. Gate resistor is affecting on the power gain, noise, and matching. Okay, impedance matching. So RG intrinsic gate resistor is RG square divided by 3 multiplied by double over L. Okay, RG double over L is the resistor value once resistivity is given, right? But since this resistivity is distributed, so we put 1/3. Okay, that's why 1/3. This is distribution effect. And there exists the extrinsic resistance, which is due to the contact resistor and any gate material. Okay, so the transconductance delay is expressed like this way. This is delay, and delay is Ri multiplied by CGS. This Ri is 1/5 GM, right? So we model like this way. But good thing is that this transconductance delay can be negligible if it is operating less than 5 FT. This is typical. But you should not neglect this. This has to be considered. Okay? This can be negligible, but still this has to be considered. Okay? So the below are Y parameters expressed in terms of those, small signal parameters, right? Okay, so you guys may just use those expression when you derive your own equation for the publication, right? It looks fancy, right? It's actually nothing. It's never ever used, but it looks fancy. Whenever you write a paper, you guys need to show off your knowledge. How can you show off your knowledge? Just to use Y parameters. 아, 야, 내가 가야 된다. 이거 켜지지. Okay, let me just for it. So as I said before, there are two important figures of merit for RF transistor, right? One is a cutoff frequency, which is defined as current gain becomes 1. The frequency where current gain becomes 1. This is a cutoff frequency, okay? Okay. So this, interestingly enough, this current cutoff frequency is not function of gate resistance. Right? Interesting. Right? So if FT is higher than 10 gigahertz, GM is not a function of IDS. Okay. So GM is fixed. So we can approximate like this way. Okay. Right. However, maximum frequency of oscillation is a strong function of RZ. Okay. Therefore, Fmax is proportional to, inversely proportional to omega, W, and inversely proportional to L. Okay. So what can we do? L is also proportional, inversely proportional to actually like this for long channel device. For short channel device, it's something like this. Therefore, we should keep this as small as possible. Then how can we improve Fmax? We need to reduce W. That's why we have to use a shorter device with a multiplication factor as large as possible. Okay. In our lab, we typically use W equals 0.6 micrometer. For certain device, it's 1 micrometer. Typically, it's less than 1 micrometer. Okay. To provide the desired width, we use lots of multiplication factor. Okay, that's how it works. Short channel device are significantly fast, right? So we introduce a new figure of error for RF application. We multiply it by FT, GM, okay? Right. So we notice that FT is a GM divided by C total. So something like this, right? So performance is proportional to scale of GM, okay? So for low power application, we need to reduce this, okay? Reduce this for better performance, okay? For LNA, you need to reduce this V overdrive voltage, okay? Okay, Pampu?
Yes, Professor.
Okay, so let's talk about noise equivalent model for MOS. Okay, so Van der Geer model is very difficult to utilize. Why? Because there is a coupling factor between IZ and ID. It's true because this model is based on the physical model. Okay, so ID and IG are strongly coupled, correlated. So, we need to calculate the correlation factor. But this is a good for analysis using computer, but better for hand calculation. So to avoid this, and we use post-Piasecki model. Here it assumes IND is independent of IZ, ING. Okay, this is a post-Piasecki. So based on this, you can make an analysis. Okay, so here for the RF application, frequency noise is typically neglected. Why is that? Frequency noise, 1 over F noise, noise of freak is Vn is proportional to WL Cox 1 over K and 1 over F. Okay, so as the frequency goes higher, this is negligible. This is much smaller than thermal noise. That's why in RF application we don't involve frequency noise at all, except mixer. Mixer, this frequency noise is unconverted, so you still have to consider. But for other application, no need to consider at all. Okay, mostly for RF application, including LNA, the channel noise is dominant effect. Channel noise is dominant effect. Okay, this is dominant. So typically gamma is 2-thirds for long channel device, and gamma is almost 1 or larger than 1 for short channel device. Okay, and also there exists a gate voltage noise from the gate resistor. So as we observed, right, noise of resistor is 4kT BR, right? Here B is 1 in analysis, right? We don't care. So what is R? R for the gate is 1/3 of right RG square and double of L, right? So that's why this delta F is just 1. Okay, we neglect. So also the induced gate current noise is like this. This is induced actually this gate induced gate current noise. Okay, IG scan. Okay, so here GG is calculated by this. Okay? This is just from the pole of the gate, because if you see this, there is a capacitor over here, right? CGS. Okay, so let's say so this is actually CD0 is C, this line, C1 over CD. Okay, so if I make a refer to input, then this current is actually 4kT GDS divided by GM. GM as a function of C1 plus F and R CGS. And this is actually GMCGS. So we neglect this. It's looking like this. And we inverse it, and it's looking like this. Anyway, this is due to the capacitor at the gate. So it's just a scale with respect to input. That's it. So when you consider the noise in the MOSFET, you typically approach in this way. This is a noise factor. This is a minimum noise factor. This is a, equivalent to noise resistor. This is a source conductance. This is a source admittance. This is optimum source admittance. Therefore, if source admittance equals to optimum source admittance, then it becomes 0. So the noise factor becomes minimum noise factor. Okay. So in typical, in this model, F min is expressed in this way. This is an arbitrary expression. Okay. Any device can be modeled with this. So F min is 1 plus 2 Rn, GC plus GS opt. Okay. So here, GC is a coupled, conductance. GS is optimum conductance. Okay. So GS opt is GS, YS opt is GS opt plus J BS opt. And it is in Gonzalez book. Okay, if you are interested in, then please take a look at this. Anyway, you just represent YS opt in this way, and this is represent the GS opt is calculated to be this. So to remove this, right, BS opt has to be chosen the negative value of JBC to cancel out this. Okay, then it becomes YS opt. The BS opt is chosen to cancel out this. Okay, F is so noise factor is ISC divided by IS. This is a source. This is combined input level current, which is IN plus VN YS scale. Okay, if you express input level noise in terms of input level noise and input level voltage. Okay, you express like this. Then here IN is IN uncorrelated, and this is a correlation admittance, and this is a voltage noise source. Okay, so here YC is VN IN divided by VN scale. This is a correlation admittance. Okay, so here VN, all of those are just extracted using simulator. Okay, this is a model, BC model, and just extract. Then you will get VN and IS. Then you can get RN from VN. You can get GS from IS. Okay. You can get GU from INU. Okay. Then you will get FN from those. Now let's consider RF MOS layer consideration. So this is a single gate contact, which means this is a gate contact. This is gate, and this is a multiple gate, right? This is a multiplication factor, M. Okay. So as can be seen here, right? If there is a single side contact, the RG is increased. If you use a double side contact line, what is RG or W? It is a one pulse of RG single. RG single. Why? Because gate length is a contact line reduced by half, and half. So this is just RG half parallel with RG up, which is 4RG. Okay. So by using double gate contact, you can reduce RG by one pulse. Okay. This is very important. To reduce, to improve the performance further. Samsung guy just introduced this approach. This is a unit cell, and this is the active component, and this is gate. Just gate is shared like this. Gate is shared like this. Okay. This is a more multiplication factor, right? Multiplication factor over 2, right? And gate connection is 3, right? Gate connection is 3. So for C, multiplication is 4. Gate connection is 5, right? So and so forth. Okay. So the result is here, right? So as can be seen, this is the example for M equal 4, right? So as a number of folded gate increases, right? This compared with the number of 2, number of 4 has a much smaller gate resistor diameter, right? Reduced quite a lot. Okay, because of this gate resistor reduction, you can achieve a much higher Fmax. Okay, maybe you guys can apply this. Okay, can apply this in your design, in your layout. See reference 4. Okay, check reference 4. This is actually similar to table structure proposed by Professor Ning about 15 years ago. MOS layout. So this is a double equal 20 micro dual well distal MOS. Layout is looking like this. This is triple well MOS. There exists the deep N well, which is this. Okay. So prevent latch up, right? To prevent latch up, we need to apply gathering over here. Gathering. That's why we have gathering. We apply here reverse bias, right? Reverse bias. So this gathering is set to ground. Passcode device layout. So passcode is this, right? This structure. So if you use two devices separately, right, then there exists a large amount of inductor between two. And also, this routing line will induce another capacitor. So to avoid this line, you guys already developed those kind of, cascode device. Another approach is this, but I don't like this because this is looking large, which will induce loss of gate resistor. So this is not okay. All right. So complete. 나 좀 늦었는데 어쨌든 여러분들 꼭 복습하시고 내 혼자 떠들지 않기를 내가 바라겠습니다. 도움이 돼야죠. 그래. 연구하는데 하여튼 적용을 꼭 해야 이게 의미가 있다는 거야. 알겠지? 수고했어요.
네, 교수님 감사합니다. 네.